Sure, sir. Sure. Fine, sir.
So now I request our Professor K. Prasad, Assistant Professor of the Department of Mechanical Engineering, to introduce our case for the gathering. Prasad sir, please, sir.
Okay. Good evening to everyone. I am Mr. K. Prasad, Assistant Professor in the Department of Mechanical Engineering at Adi Shankara deemed to be University, Guduru, Andhra Pradesh. It gives me a great pleasure to introduce our distinguished resource person for this session, Dr. S. Vedharaj, Assistant Professor in the Department of Mechanical Engineering at the National Institute of Technology, Tiruchirappalli, Tamil Nadu, India. He received his PhD degree from the National University of Singapore, NUS Singapore. He was a postdoctoral research fellow at the Clean Combustion Research Center, CCRC, King Abdullah University of Science and Technology, KAUST, Saudi Arabia. He has more than 10 years of research experience in the field of IC engines, and he has major research area include low carbon fuels, hydrogen based fuels, low temperature combustion, partially premixed combustion, pre-chamber spark ignition system, and high efficiency combustion concepts. He has published 40 research articles in high quality journals and has been granted one US patent. Dr. S. Vedharaj received funding from Science and Engineering Research Board, SERB, under the Early Career Research Award, ECRC scheme, and from NITT under the Institute seemed granted scheme to establish Clean Combustion Laboratory, a research laboratory at NITT for performing fundamental spray and flame characterization studies. On behalf of the organizers and all participants, I extend a very warm welcome to you, sir. With these words, now I hand over the session to our esteemed resource person, Dr. S. Vedharaj sir.
Thanks for the nice introduction. And I'll share my screen, so kindly let me know whether it's visible to you. So it's my slides visible?
Yes, sir.
Thanks. Right. Before I start, I'll just want to formally thank Dr. Manoj Kumar as well as Dr. Michael Joseph Stalin for taking initiative and organizing this kind of ACT ATAL workshop or faculty development program. And that too, the topic for today is on smart transition for a greener tomorrow, majorly concentrating on innovation and energy and sustainability. And I thought I'll present about the role of hydrogen and ammonia for a sustainable transportation system. I believe that taking a lecture late in the Friday evening is a bit inconvenient for many, right? But still, I made the presentation in such a way that it might engage you with some general facts, and also will touch on with the technical aspects of how hydrogen and ammonia can be adopted for the transportation systems. So my presentation outline is goes like this. So we'll start with the general background, and then we'll also discuss about the future powertrains and what are these zero carbon alternative fuels and what are its characteristics, and what are the fundamental understanding about these fuels, and how these fuels can be adapted for internal combustion engines. And we'll also touch about certain advanced combustion concepts which I'm currently working on, as majorly with pre-chamber spark ignition system. And we'll also discuss some things related to RCCA engines and onboard ammonia reforming. And I'll just introduce about the different concepts, and finally we'll have concluding remarks as well. So to start with, this comes to my mind, right? Whenever we see a news article, we ended up in seeing these things. So is it an end to an IC engine? So the end of internal combustion engine, death of internal combustion engines, and it's quite evident, and people are having a view that the technology that has been developed 100+ years ago, and still there is nothing much to be improved. And uh, thing is, there is nothing much with internal combustion engine. That's what the opinion is all about in the general public. And European Union also just reaffirmed that they go with the ban of new cars with internal combustion engines by the year 2035. And so that's the current scenario. And now European Union was the only one which sticks on with these stringent wordings. And after the declaration by the European Union, and many people in the European Union, right from Italy, Germany, they are thinking about internal combustion engine bans, as well as the BMW CEO. He recently mentioned in the last week or so that combustion engine ban is a big mistake. Seeing the sales that they got in the 2025, and there are a number of news articles coming on this side as well, right? And it's kind of quite confusing scenario, and we are not sure what will be the future. We are sure that people are investing on electric vehicles, and the electric vehicles are moving ahead at a faster rate than expected. But what about combustion engines, and what is the problem with the combustion engines? So I just thought we'll discuss about the problems. Why IC engine is not preferred by peoples or economists or environmental peoples. Why? The reason is everyone believes that IC engine releases more toxic emissions, and you can't achieve a zero emission vehicle with internal combustion engines. But they claim that battery electric vehicles is a zero emission vehicle. But if you see from the life cycle analysis or well to wheel analysis, battery vehicle still has more emissions than your internal combustion engines. And depletion of fossil fuels, right? So because we are relying on fossil fuels, and it is a natural resource, so obviously depletion of fossil fuels is one of the major point that hinders the IC engine usage, and majorly the country's self-dependency. So we are all relying on foreign oil for the transportation sector. And recently we have gone through these things. When Russia and Ukraine had a war, the European Union faced drastic problems in getting the natural gas and so on. So if we could develop some kind of technology for individual country, then it might help them in executing their plans, and without the dependence on other countries. The final one is we do have a problem with the global warming and greenhouse gas emissions. So the carbon footprint has to be reduced to a greater extent. So that's what is all about. So I thought about it, and I just found out these are the 5 major reasons why IC engine is not preferred. And first, if you see the IC engine releases toxic emission, true, it releases toxic emissions, but it is regulated by the legislation boards, and it started in the year 1993 with Euro 1, and we are currently in Euro 6, and Euro 7 is in the next phase. In Euro 6 itself, we had 2 or 3 different phases. And India currently, we are adopting Euro 6, and we are following Bharat Stage 6. And if you just compare the amount of emission that is being emitted by the automobiles from 1993 to 2020, the reduction, I just plotted 2 different emissions. One is with respect to nitrogen oxide, and one is with respect to your particulate matters. So the amount of reduction that we are able to achieve is nearly more than 95%. So nowadays we don't see cars or vehicles emitting black smokes. And the I also have a funny video which Audi has released, right? So a person want to commit suicide, and he entered into the car and he connected his tailpipe to his inside cabin, and he turned on the engine and he left it full night so that the entire fuel gets out. And he was in opinion that he'll be died because of the emissions. And to his surprise, he was alive in the morning, right? So Audi released these kind of funny videos, and they say that we produce clean engines, right? So now with Euro 6 or BS6 and BS7 vehicles, the amount of emissions that we leave into the atmosphere is quite low. And yeah, so the past 3 decades, it has reduced drastically. And the major reason behind that is the advancement with the electronic systems, and how electronic system aid in optimizing your engine performance and so on. And next is zero emission vehicle is not possible with internal combustion engines. True. And I went to a conference in Japan in the year 2018, and Honda presented these things, right? So instead of claiming it as zero emission vehicle, they claim it as we produce engines which has minus emissions. So minus is better than zero, right? So people started different terminologies to promote their concepts. These kind of presentation is to say that the engines are clean enough, right? So they drove the Honda car in Los Angeles highway, and they measured the hydrocarbon concentration in the inlet as well as in the exhaust. And they found that the exhaust has lower hydrocarbon concentration than the inlet. So which means you feed in your gases and you can clean the metro cities, highly polluted metro cities, with internal combustion engines. So the reason is we have, in order to meet the emission legislations, there is a number of after treatment systems and optimization of combustion strategies, which reduces all the emissions to nearly 99 or 98%. And whatever it's left out into the atmosphere is clean. So they proudly claim that you can use hydrocarbon to clean your metro cities as well. So depletion of fossil fuel, yes, we do accept. And whenever they make a prediction, right, they say that the peak is soon, and after these peak, the oil production will be getting to a lower side, right? And I closely work with Aramco. Aramco is one of the leading oil manufacturing industries. And we had great discussions, and we get to know that there are still more reserves has to be explored as well. And they haven't touched the Arctic and Antarctic oceans. So if they go on with exploring oil in these regions, they might survive for the next 50 or 100 years. So that was the comment. But still, we have to accept the fact that the depletion of fossil fuel will happen. If not today, it will happen in some days soon. But when it comes to prediction, people say that. I also have a clip on 1919s, right? So people say that the prediction is soon, right? The peak prediction is soon, and they climbed it in 1919. I also have in 2010. So which means nearly 100 years, the prediction is saying that the peak oil is reaching, the oil resource is reaching its maximum limit soon. But we have to accept the fact that one day or other, these resources will be getting depleted. So we need to find some other alternate means as well. And when it comes to global warming and greenhouse gas emissions, so if you take the entire sectors, the transportation sector corresponds to only 22% of the global CO2 emissions. And about this 22%, you can see the light vehicles, automobiles contributes to 40%, and heavy vehicles to 34%, and the remaining is by marine and aviation and railways. So if you see combustion engines, you are feeding in with hydrocarbons. So if you have a ideal combustion scenario, that is, you have an efficient engine which is capable of combusting 100%. So it is kind of ideal engines. Even with that, if you take hydrocarbons and combust it with air, you produce carbon dioxide and H2O, right? So these two gases are the greenhouse gases, right? So it is like people don't care much about H2O because that can be brought down as rain and things, but CO2 be retained in the environment for many years, and it absorbs the radiation and re-radiate into your Earth's atmosphere. So it causes global warming. So our ultimate objective is to reduce the global warming. But even with 100% efficient engines, global warming is still a problem. So roughly, if you see all the five problems which I have listed down, the major things it counts to be only the global warming and greenhouse gas emissions. And the second thing is, the first most major thing is the country's self-dependence. So we have to plan in such a way that the country can be self-dependent for its transportation and the energy sector. So, but if you go with battery electric vehicles, it doesn't solve the problem because we need to rely on China for the lithium resource, and there are a number of complications associated with it. So we need to find out an immediate solutions, right? So what might be the alternate powertrain for the future transportation sector, right? So shall we go back to the older days? Either we can walk around or running, and or shall we adopt to using carts to travel from one place to another? And we'll see what happens when we walk or run, right? So there was a study which says that in order to have a replacement for the commercial vehicles, people can walk or run or they can do cycling, right? So if you just compare the scenarios, the amount of CO2 emission, because as humans we also emit CO2s, right? So the CO2 emission depends upon the economic growth, which means it depends upon what food habits that we accommodate. So India is on the lower side because we are mostly vegetarians and we go with light foods. So the amount of CO2 emissions that is being emitted by a person in Indian regions is only about 0.5 or 0.05 or 0.06 grams of CO2 per kilometer of walking or cycling, right? And if you go with other high economic groups of United States or European Union, it is about 0.28 or 27 kilograms of CO2 per kilometer of cycling or walking. So now if you see what is the average CO2 emission for a passenger car, so it is kind of roughly about 0.12 to 0.2 kilogram of CO2 per kilometer. So which means that you can carry at least a minimum of 4 or 5 passengers inside the passenger car. So it is kind of 0.04 or 0.03 if you are transporting an individual person, right? So which gives opinion, right? Even if you walk, you are emitting more CO2 than driving a car. So I'm not saying you should not go for a walk or cycling, but the statistics says that the amount of CO2 emission that we leave out to the atmosphere is quite higher than the passenger car if you take it as a group, right? And this is a clip from the streets of London in the year 1908 or 1910. So the problem before the century is same emissions, right? They had 200 meter cube of liquid emissions per day and 100 tons of solid emissions per day, and they used the horse carts and bullock carts, and even the dead animals was hard to remove from the roads, and thousands of army people were involved in transporting these emissions out of the city because it's kind of polluting the entire city, and people couldn't able to live in the city with all these liquid and solid emissions. And on that scenario, and 19th century or the early 20th century, the first IC engine driven vehicle was seen as a significant environmental solution. People were very much happy that they are free from all this emission statistics or emissions problems, right? Now coming to period after 100 years, right? 100 plus years, we say that engine emission is a major concern, and we are looking out for new solutions. And whatever the alternate technology that they propose with respect to battery electric vehicles and hybrid vehicles, everything has been evolved long back, right? So it is not new to the nations. All these powertrains has been invented when the ICE engine was invented, right? And ICE engine has a quite high versatility to adapt for different conditions and to take up different loads with the short time frames. So that made it to survive for the last 100 plus years. And if you look back, ICE engine is the major contributor for the industrial revolutions, and because of which all the workloads with the manual work as well as the work involved with the horses, everything has been replaced with machines powered by internal combustion engines or electricity driven things. So now we have to look for the future powertrain, and we have to select suitable powertrain so that after 100 years we should not look back and see so it is still creating a problem, right? And the probable alternate solution for the current scenario, we can have alternative fuels. Initially, people started with different kind of biofuels, and now the situation has evolved in such a way that there is not much requirement with respect to biofuels. People are more keen on going on with zero carbon fuels. You use biological resources, but we need only zero carbon fuels. We are not interested in carbon, right? And battery electric vehicles. So you can have a complete battery electric vehicle, or you can go on with hybrid vehicles. So there are two different types of hybrid vehicles. One is the plug-in hybrid, and another one is you can have hybrid powertrain with either a fuel cell or the ICE engine as the range extender. And there are also certain advanced ICE engine concepts that are evolving, and the efficiency of that engine is quietly near to 60%. Right, conventional engines go with 35 or 40% efficiency. So this advanced ICE engine concepts can achieve 60% efficiency and can be a suitable option in the near future as well. So among these alternatives, if you see what is the better alternative in the current scenario, so one is your alternate fuels. So you generate some kind of zero carbon fuels and use it in your existing powertrain system. So you don't require any modification to the existing layout, right? So you don't require any charging stations. You don't require higher investment on the infrastructure, right? So most of these zero carbon fuels can be adapted to ICE engine powertrain with slight modifications, right? And second thing is hybrid powertrain. So hybrid powertrain is quite advantageous as it allows the engine to operate at the maximum efficiency point, and the load fluctuations can be met with the electric motor as well. So when ICE engine performs at a lower efficiency scenarios, that can be compensated with the electric motor. So we can go with some kind of smart hybrid powertrain, wherein ICE engine can be used as a range extender. And next is the advanced ICE engine concept. The reason is you can develop fuel cell technology, or you can develop battery vehicle technology, but the problem is it is like a kind of scenario where you have to completely change the entire industrial structure itself. We have an automobile industry, and there are a number of ancillary industries which provides the supplementary components for the automobile industry. So everything is well established. So if you want to do a small hardware change for adapting these kind of zero carbon fuels, it is widely easy to implement, rather than going on with developing a new kind of industry and investing much without knowing what will be the future. So it is quite um, tricky, and the future is not known to everyone, right? So better option in the current scenario is you go for low zero carbon fuels in a hybrid powertrain. So with high efficiency ICE engines as a range extender. And recently, Akio Toyoda, the president of the world's biggest automaker, Toyota Motor Corporation, he said carbon is our enemy, right? And not the internal combustion engine. So whatever you given, it will burn. So if you give in clean fuels, it will burn and it will generate zero emissions as well. And if we look back to the initial discussions that ICE engine is banned in European unions, and the West is keen on moving on with electric vehicles, whereas the Japanese as well as Koreans as well as these giants, automobile giants, they haven't declared that they are banning ICE engines, right? So they have a wide open path, right? So because the future is unknown, people are investing on electric vehicles, people are investing on fuel cells, people are investing on advanced combustion concept, wherein the engine efficiency is targeted towards 55 or 60%, and zero carbon fuels, how to adopt these kind of zero carbon fuels in engines. So people are looking around for all these different options. So as a wise man, it has to be open to everything, right? How it evolves and how it sustains in the long term, it's still a question mark. So it has to have wide open options, and we can't completely neglect internal combustion engines. So with that, we'll see what is the adaptability of zero carbon fuels in internal combustion engines. Today, majorly, I'll discuss about two different zero carbon engines. One is hydrogen and another one is ammonia. What are its combustion characteristics? How far this can be easily integrated with the existing powertrains, and what difficulties we have, and how the advanced combustion concept adopt these kind of zero carbon fuels, right? So that's the agenda for today's talk. So when we talk about hydrogen and ammonia, we know it is H2 and it is NH3, right? So there is no carbon involved, so it is kind of a clean fuels. We don't get unburned hydrocarbon emissions, carbon monoxide emissions, CO2 emissions, and there's no sulfur dioxide emissions. So everything is clean, right? So you get only water vapor as the major emissions if you combust. And if your temperature is high enough to support the formation of nitrogen oxides, because nitrogen and oxygen dissociate at a temperature higher than 2000 Kelvin, right? So if the combustion temperature is higher than that, then there will be some NOx formations, so which has to be avoided. There are a number of strategies that can be used to reduce your NOx emission as well. And when we look into the properties, fuel properties of hydrogen and ammonia, it best suitable for engine operations, but they have higher octane numbers. So when you have higher octane number, it's best suited for SI engines, but people try to use it for CA engine as well, in kind of dual fuel mode or RCCA combustion modes. Hydrogen, when we talk about hydrogen, hydrogen has wider flammability limits, and it requires lower ignition energy, right? So these kind of wider flammability enables SI engine operations at a leaner mixtures, and we can also achieve stable combustion with better performance as well. So when we are, the world is moving towards gasoline lean combustion. And with gasoline lean combustion, when we go with the lean limit, you have to go on with higher ignition energy requirement, right? So if you adopt hydrogen in case of gasoline, and we go with lean scenarios, that is more amount of air and less amount of fuel, then the combustion will be complete, and hydrogen also require lower ignition energy, so it aids in achieving stable combustion with lean operation as well. And one thing is you have to modify your fuel storage systems. So instead of having the fuel tank, you need to have some kind of cylinders, and the fuel injection system has to be a gas fuel injection system because hydrogen exists in gaseous media. And we also had a problem of backfiring. So in order to avoid backfiring, we have to install some kind of flame arresters, and there are different strategies to avoid the backfiring as well. We'll just see that in the coming slides as well. And hydrogen is kind of fuel which has higher energy density on mass basis. So it is about 120 kilojoule per kg. So that is the energy density of hydrogen in mass basis. And compared to your conventional gasoline or diesel fuel, it is almost 2.5 times higher in terms of mass basis. But uh, we know when we store gaseous fuel, it is quite problem, right? So the volumetric energy density of hydrogen is too low. It is almost 1/10th of your gasoline engines. So we need to have adapt large pressure storage systems, and the hydrogen vehicles developed by Ashok Leyland and other truck manufacturer, they are keen on going on with 350 bar as the storage pressure of hydrogen. And people are also researching about 700 bar storage pressure. So if you could store hydrogen at 700 bar, so the energy density is quite equivalent to that of the gasoline, the entire tank, right? So they are looking for 700 bar. So now that can be achieved with the modern advanced materials, the carbon nanofibers, and a number of scenarios. But thing is, if you are taking a hydrogen of this much quantity in a vehicle, it is like having a hydrogen bomb in your vehicle, right? So the major challenges is you need to have a safe storage, and you need to ensure it is properly transported, and the handling as well. As I said, it has wider flammability limits. So if it leaks into the atmosphere with a small fraction of hydrogen, the ignition may happen. So it is kind of quite tricky in terms of storage, transportation, and handling. And when we use these hydrogen, it is also results in metal embrittlement, right? So when metal surface is exposed to these hydrogen for a longer time, so the hydrogen makes the metal as brittle as possible. So we need to have some kind of different coatings to avoid these kind of metal embrittlements. So now people have started seeing ammonia as a hydrogen carrier, because if you see into the molecular structure of ammonia, so it is like you have 3 moles of hydrogen stored in that things. And ammonia exists in liquid state itself. If you just pressurize to about 10 or 11 bar at atmospheric temperatures, you can convert ammonia into liquid. So once you are able to convert the fluid into liquid form, then storage is not an issue. So transportation is not a problem, and handling is not a problem. So ammonia have a upper hand in avoiding the challenges associated with hydrogen. But again, there is some problems associated with ammonia as well. So you have narrow flammability limit, right to opposite of what we discussed with hydrogen. The flammability limit is very narrow, and it requires higher ignition energy, and the flame speed is also very slow with ammonia. So it is kind of a difficult ignition process that has to be accomplished when you use ammonia in engines. And ammonia combustion may lead to NOx emission as well, because you have fuel-bound nitrogen. So that nitrogen will react with your oxygen in the high temperature regions, and it might lead to form NOx emissions. And there are also scenario that some ammonia might doesn't take part in the combustion process, and it might come out as such. So ammonia is kind of a toxic gas, and it is kind of corrosive environment, right? So it is not a quite cakewalk to adopt ammonia in engines as well. So it is kind of still challenging scenarios. And this slide presents you the property comparison of hydrogen and ammonia with the conventional fuels like gasoline, diesel, and natural gas. So the major thing is, if you see the octane number, so these ammonia and hydrogen qualify as your SI engine fuel, and the gasoline octane number is about 90 to 98, whereas the octane number of these two is above 100. So it is 130 and it is 110. And when we talk about the lower calorific value, ammonia has a lower calorific value on mass basis, as well as hydrogen has a very high calorific values on mass basis when compared to your gasoline or diesel. But if you see on the energy density on the volume basis, so it is roughly about 11.3 for ammonia compared to 31.5 for your gasoline, and hydrogen is only 3.5. So there are a number of things that has to be compensated. And when we talk about the minimum ignition energy requirement, the ignition energy required by hydrogen is way less than your gasoline, whereas your ammonia requires higher ignition energy. And we store ammonia as liquid, so it has higher latent heat of vaporization. So once it enters into your engine, it is sprayed into the engine, it absorbs the heat from the surrounding air, and it brings down the combustion temperature. So which might aid in reducing your NOx emissions, but still it is way higher than your gasoline. So it's almost 6 times higher than your gasoline scenarios. Right, different properties of hydrogen. So you have higher flame speed, you have higher octane number, you have higher auto ignition temperature, wider flammability limits, heating value is quite a problem, right? So all these things provide a flexibility to design your engine in such a way that you accommodate, uh, you fine tune your engine parameters such a way that it's highly efficient, right? So you can modify the compression ratio because you have a higher octane number, so you can increase the compression ratio without engine NOx scenarios in SI engine itself. And you can hydrogen engines can be operated at a higher compression ratio of about 13 or 14 compression ratios. And you need to have highly durable fuel injection systems, and we need to have a pressure regulator separate, and the hydrogen cylinder which is capable of handling hydrogen at very high pressures. Right? And when we talk about ammonia characteristics, so it is considered as a hydrogen carrier. So you either burn ammonia as such, or you can crack ammonia. So liquefied ammonia has about 106 kg of hydrogen per meter cube. So that's much amount of hydrogen can be carried by ammonia. So the general process for producing ammonia is by Haber-Bosch process, and the cost associated with the production is quite reasonable, and it is quite less compared to your gasoline as well. It's competitive with gasoline. And as you can easily convert that into liquid at a slightly higher pressure of about 1.1 megapascal. So it is easy for handling and storage. And distribution of ammonia is well established because people use it for as a fertilizer, and they use it for refrigeration systems and different industrial applications. They require ammonia. So the transportation or distribution is well established. And if you want, you can go on with onboard reforming of ammonia, wherein you use some kind of catalytic converters, reformers to convert ammonia into hydrogens and use it in applications. And if you combust ammonia, you get very low emissions, and compared to hydrogen, it has higher energy density as well. But the challenges is it is associated with higher latent heat of vaporization, and it has higher auto ignition temperature and lower flame speed as well. Just a second. Now, the fundamental characterization of these fuels, right, and compare it with octane and methanol. So the green color represents your ammonia, and the blue color represents your hydrogen. Right? So if you see the auto ignition delay or ignition delay of these fuels, ammonia has higher ignition delay, whereas your hydrogen has lower ignition delay. And the adiabatic flame temperature is also highest for hydrogen, and it is lowest for your ammonia scenarios. And the laminar flame speed, it is quite fast for your hydrogen, whereas it is very much slow for your ammonia engine. So when you have higher flame speed, it is like your SI engine is operated, and the heat addition in your SI engine has to be at constant volume. So if you have a higher flame speed, then it is ideal to achieve constant volume heat addition. But with commercial gasoline, it is not exactly constant volume heat addition. But with hydrogen, we can achieve constant volume heat addition. And the extinction strain rate is higher for hydrogen, whereas it is lower for ammonia. So it says that how the flame get extinguished when it is near to the cylinder wall. So hydrogen and ammonia has completely different properties, right? So it is kind of, one is very fast and very active, whereas another one, ammonia, is kind of a lazy fuel. It doesn't combust at a faster rate, right? So there are scenarios many people have tried, like mixing hydrogen and ammonia in different proportion and tried evaluating the combustion characteristics and so on. So with the fundamental, because if you have lower ignition delay and if you have faster flame speed, then your combustion will be at a faster rate, and you finish the combustion in a very short span of time, and it aids in your performance improvement. So we'll just move on with the engine studies with hydrogen. So hydrogen can be introduced into the conventional SI engines by three different ways. One is you go with the carburetions and technology, or you go with port fuel injection system, or you go with direct fuel injection system. And carburation and port fuel injection system is both you inject the hydrogen into the inlet manifold and you allow the fuel air mixture to enter into the combustion chamber. Whereas the direct injection system is kind of having a injector directly into your combustion chamber. So you inject hydrogen into the main combustion chamber. So hydrogen direct injection offers several benefits, because people have tried carburation and port fuel injection for hydrogen a number of years before. So it is a well-established scenario. Hydrogen can be easily adapted into these kind of carburetor or the port injection systems. But hydrogen direct injection is quite advantageous than these two things. So you have a accurate control over what is the amount of fuel that you inject into a particular combustion cycle, and you can inject in such a way that the fuel is stratified and can get proper combustion, 100% or 98% efficient combustion scenarios, which will increase the power output. You can increase your fuel efficiency. So combustion is proper. Again, you go with the reduced or decreased emission levels. And the major thing is you can avoid the risk of backfire. So as I said, with carburation as well as in port fuel injection system, backfiring is the major drawback. And with hydrogen direct injection, you can completely avoid the backfiring, and there is no problem in these things. But implementation of hydrogen direct injection is challenging, right? You require high pressure gas injectors, you require high pressure storage tanks, you require high pressure distribution lines as well. As we know that hydrogen may cause embrittlement, metal embrittlement, we have to ensure that the material that we use is highly compatible for hydrogen scenarios. So 100% hydrogen in conventional SI engines may lead to pre-ignitions, and people prefer to go with lean mixture, because conventional SI engine is operated at stoichiometric conditions, And if you go on with the stoichiometric scenario, then pre-ignition is one of the things that will definitely happen, and it will deteriorate your engine scenarios. And people, in order to avoid that, they go with lean mixture. So here is a kind of scenarios where the hydrogen usage 100% has led to pre-ignition, right? So you could see that this is cycle number 60. So it is measured for the continuous engine operation, and in cycle 16 the engine was operating with normal combustion scenario. In cycle 22 there was a slight knock, right? So the pre-ignition happened earlier, so it just moved this side, and that keep on accumulating. And in the cycle 32 there was a scenario where the ignition happens before the closure of inlet valve itself. So when you have ignition happening before the closure of inlet valve, the backfiring happens. So in order to avoid this, you have to go with the pre-ignition limit. So you can't operate a hydrogen in stoichiometric conditions. So you have to go with kind of lean scenarios, and it also depends upon the injection timing, right? So the injection timing will give enough time for mixing, and it can also provide a cooling off period. For example, if you inject hydrogen in the say engine at 220 degrees before the top dead center, which means closer to the bottom dead center, at the end of your intake stroke you are injecting. And if you just move on till the bottom dead center, the pre-ignition limit can be reduced. It can go till from 1.42 to 1.34, right? And once you reach beyond that, then the mixing is deteriorated, and again the pre-ignition limit goes to a higher range. So people suggested to have the injection timing as 180 crank degrees before the top dead center. And if you want if you feel that the mixing is deteriorated and the time is not sufficient for injecting your hydrogen, then you can go with two fuel injectors in your cylinder and inject a huge amount of hydrogen in a short span of time. And thing is, when we go with lean mixtures, obviously the temperature associated with the combustion process is reduced a lot, and thereby the NOx emission is reduced. So if you go with 1.3, it is a bit higher, and when we go to 2.3, it is reduced a lot. Some design consideration for hydrogen SI engines. So when we specifically design an engine, SI engine for hydrogen fuel, we need to take into account few points. One is you have to adopt cold rated spark plug, which means the spark plug, whenever after the ignition, that electrode will not get heated up, and once you don't have any hot spots inside, it will avoid the auto ignition. And we also have to select a spark plug with smaller plug gap. Usually the plug gap is about 0.8 millimeters, and with hydrogen engines you have to go with 0.5 or 0.25, so that the ignition voltage or the ignition energy that we feed in can be reduced. And we also properly ground the spark plug so that the residual ignition energy should not be introduced, and it should not lead to some kind of uncontrolled combustion scenarios. And we need to provide proper cooling so that we ensure that the injection is properly timed. So it is kind of scenario that we doesn't allow the hydrogen to get accumulated in the intake manifold. So whatever is being injected, it will enter into that cycle in that particular cycle. So that has to be considered, and we need to avoid hot spots inside the combustion chamber. So for that, you can go with either multiple wall systems or provide additional coolant passages, or you can increase the air cooling period. As I said, you reduce your fuel injection timing during the intake stroke and allow the air to flow through so that it will hit on the cylinder surfaces and cool down the things. And we need to ensure that proper scavenging is done, so no residual gases from the earlier cycle is retained within the combustion chamber. And usually the hydrogen flames, the quenching diameter is too low, so that the flames can enter into the piston side surface as well. So you have to make sure that the piston top land clearance is too small, so that the hydrogen flame propagation into the annular gap, that is the crevice region, is reduced. And we need to select proper wall seat and injector material, because hydrogen may result in embrittlement of these materials as well. And hydrogen may leak, or it might, you might have heard about the blow-by losses, right? So from the cylinder, it might enter into your lubrication oil or the crankcase at the bottom. So that will combine with your lubrication oil. It might deteriorate your lubrication oil. So we have to select a proper lubrication oil that is compatible, and we have to give positive crank ventilation as well, so that the blow-by hydrogen is not accumulated inside the crankcase. If that is the case, in case of any hotspots, it might auto-ignite. And it provides higher flame speed and higher octane numbers, so you can go on with designing the engine with higher compression ratios. And flame speed is too fast, so you don't require too much turbulence inside the cylinders. So you can design it in such a way that the turbulence inside the engine can be reduced. So these are all few design considerations for hydrogen SI engines. Similarly, ammonia can also be adopted in the conventional spark ignition engines. So here is a study with different fuel combination. One is fuel A is your pure ammonia. Fuel B is hydrogen, 15% hydrogen enriched ammonia. And third one, fuel C, is your complete methane, right? So we take methane as a reference. And you could see that the pressure curve for methane is quite higher when compared to your hydrogen and ammonia. So more or less the pressure curve is similar for these things. And we optimize the spark timing such a way that each fuel gets its maximum brake torque conditions, right? So the ignition timing is quite advanced for ammonia, whereas it is retarded for your hydrogen as well as your methane, right? And the pressure rise rate and heat release rate has a higher magnitude for methane compared to your ammonia and your hydrogen, right? And here this shows the ignition delay, right? And this shows the combustion durations. And we could see that methane has lower ignition delay as well as combustion duration, whereas ammonia has higher ignition delay. So the initial combustion initiation phase is quite longer for ammonia compared to other fuels. And with hydrogen enrichment, so the star mark is with hydrogen enrichment, you could see that there is a huge difference, right? For 15% addition of hydrogen, the ignition delay is reduced a lot, right? And the combustion duration for ammonia and methane, if you compare it lean scenarios, it is almost 10 crank angle degrees, which is quite long. So as I said before, ammonia has lower flame speed, and its auto ignition is also very poor. So that's the reason why we get these kind of behaviors. And coming to the emissions from ammonia engines, major emission that we are interested or we need to consider is your NO emissions, nitrogen oxide emissions. So usually for conventional SI engine with gasoline combustion, the peak of the nitrogen oxide formation happens near stoichiometry, whereas here it is shifted slightly to your lean side. It occurs around 1.3 of excess air ratios, and NO2 emissions peak after that. But in SI engines with conventional gasoline, both occurs near to your stoichiometric scenarios, and here it is kind of too much lean. And the chemistry of NO2 and N2O is linked with ammonia combustion, right? So here this graph shows the ammonia combustion for 3 different compression ratios. Quite surprisingly, with the increase in compression ratio, the ammonia emission is higher, which means the ammonia is not taking part in the combustion process and it is left out into the exhaust gases. And if you look back into the reason why it is happening, So it is like when the compression ratio is higher, the pressure that we encounter inside is higher, right? So it is kind of pushing all the unbound gases to the regions near the piston land surfaces. And during the expansion stroke, these gases is left into the cylinder and it moves out to the exhaust gases. So that's why with the increase in your compression ratio, there is an increase in your ammonia combustion. And ammonia combustion is related with NO2 and N2O chemistry. Usually N2O is not a problem with diesel combustion. And also here, if you take ammonia combustion at stoichiometric or less lower excess ratio conditions, it is only about 10 or 20 ppms, right? So which means that the concentration of N2O is quite low. But if you operate it at higher lean conditions or under excess air conditions, it becomes a significant emissions. N2O is also a greenhouse gas, right? So, and it has a potential higher than your CO2. So we need to make sure that N2O is not being released during the combustion process. So we need to optimize the chemical kinetics of the ammonia combustion in such a way that it doesn't release too much of N2O. Right? And for pure ammonia in IC engine has different drawbacks, as we discussed: higher auto ignition temperature, higher latent heat of vaporization, ignition delays longer, and flame instability, higher nitrogen oxide emissions. So all these things makes challenging. Ammonia combustion in IC engine is challenging, and also we need to see to the emissions of ammonia and N2. Ammonia is toxic to human beings, and N2 has higher global warming potential. So adopting these ammonia as well as hydrogen in existing engine platform is quite easy, but if we want to avoid all these things, we have to go with some advanced combustion strategies, right? So we'll touch about certain advanced combustion concept, not majorly one or two here. So we all know that the conventional combustion concept, SI, CA, and HCCA is also quite long. So there have been decades of research on HCCA engine, and recently people have started commercial implementation of HCCA engine as well. So I consider these three to be your conventional combustion modes. The SA engine is quite clean, right? So we have a three-way catalyst, so there is no emissions. All the emission levels emitted by SA engine is quite low. But when we operate SA engine at part load or low load, the efficiency is low. CA engines, we know we operate it at higher compression ratio, so the thermal efficiency associated with CA engine is quite high. But on the drawback, you have higher NOx and soot trade-off. HCCA engine is combination of both these things, right? So it goes with higher efficiency and achieve lower NOx and soot emissions. But the problem is you don't have a control over the combustion process, and the power density is also too high when it comes to HCCA engines. Now we'll discuss about two advanced combustion concepts. One is pre-chamber spark ignition engines. So it is kind of you remove the spark plug from the engine and replace it with a small chamber. So the small chamber is equipped with the spark plug as well as an injector. So you generate some kind of rich mixture inside this regions and you ignite it, and the flame generated will be dispersed to your main chamber. So main chamber is equipped with lean, and you can combust the lean mixture with these ejected flame structures. And other type is similar kind. You go with RCCA. So RCCA, you inject low reactivity fuel in the intake manifold, and the low reactivity fuel is engulfed into the main combustion chamber, and you use some kind of pilot injection so that the combustion happens and everything burns all of the sudden. So to initiate the combustion process, we use some kind of pilot injection. So mostly high reactivity fuels is used as pilot injection scenarios. So we'll discuss about the pre-chamber spark ignition systems, engines, and how ammonia can be adopted with these things. So PCA system, there are two different types. One is passive, another one is active. In passive, it is like the air fuel mixture in the main combustion chamber and pre-chamber is more or less same, right? The proportion is same. And in active, we have a separate fuel injector in the pre-chamber so that some kind of rich or stoichiometric mixture is maintained in the pre-chamber, whereas lean or ultra lean mixture can be generated inside your main chamber. So which provides higher flame intensity so that flame can combust lean or ultra lean mixtures as well. The major advantage with the pre-chamber system is you can achieve stable combustion. You can go for very ultra lean combustion so that your combustion efficiency can be improved a lot. And the flame jets that is ejected from this pre-chamber is travels at a higher speed. So you create a number of ignition sites, and the combustion rate is also faster, and the flame area is also higher compared to your conventional SI engines. And majorly, when we talk about pre-chamber system, the flame jet, that is the important one, and different operating and design conditions will influence the flame structure, right? So the major parameters you can broadly classify it as the structural parameters of the pre-chamber and also the operating conditions. So you can optimize the pre-chamber volume, nozzle hole diameter, number of nozzle holes, what orientation it can be, and what is the throat diameter, what is the shape of the pre-chamber. All these things can be optimized to get an optimum design and operating condition. In operating condition, you can vary the different operating conditions. And finally, it can be implemented in engine systems. So you get higher efficient engines with ammonia combustion, because ammonia is a kind of sluggish or lazy fuel. So you require some kind of ignition source to activate these things. So pre-chamber is seen as the effective means. Right? So this video shows a comparison between the flame propagation in SI system and PCSI system. This is taken in our lab, wherein we can see that the flame propagation is quite very slow in case of your SI engines, and by that time the flame is very much fast with the pre-chamber systems, and it engulfs the entire combustion chamber. So thing is, you can achieve faster combustion. We have tested it with a single nozzle hole, and if you have a multiple nozzle hole, the rate at which the combustion happens will be quite fast when compared to your SI engine. So it's kind of scenarios which is much needed for the sluggish fuels like ammonia. And we did analysis of different combustion characteristics under SI as well as PCSI mode. So what we could see is we did it for 3 different fuels: hydrogen, ammonia, and methane, all gaseous fuels. And hydrogen outperformed everything in terms of the combustion characteristic in SI engine mode. And when we go to PCSI mode, the same trend repeats with hydrogen performing or showing better combustion characteristics. But the improvement that we see with SI and PCSI, the improvement is much higher with ammonia rather than with other methane or hydrogen system. Hydrogen is highly reactive. It's already it is capable of igniting at a faster rate. So the higher ignition system, incorporating higher ignition system doesn't vary much, right? And whereas with ammonia and methane, it is its influence is much higher. So there are different ignition mechanisms. That is, one is with the jet flame ignition, so wherein the individual flame develops a spherical flame and it expands in through all the nozzle holes. So that is called as jet flame ignition. Next is jet ignition, so wherein the flame is kind of elongated. So you have a very small nozzle hole so that the flame, the combustion products enters into the main combustion chamber and it generates an elongated flame or overstretched flames. And next is kind of jet wake ignition. So wherein the combustion happens in the pre-chamber and all the combustion products is ejected into the combustion chamber. So the blue color represents the concentration of combustion products, right? So all the combustion products exist, enter into your main chamber, but the flame doesn't happen here. What happens is near to the nozzle regions, you have higher temperature scenario, and the auto ignition or ignition of the air-fuel mixture happens here. And dual jet ignition is a kind of combination of your jet bag ignition and jet ignition. So these different ignition mechanism can be accomplished by optimizing your design parameters of the pre-chamber nozzle holes and the pre-chamber geometries as well. So this is how the system looks like, and this is a CAD drawing of the active pre-chamber systems, wherein we have the pre-chamber injector and we also have a spark plug installed in the pre-chamber, right? And during the intake process, you allow the gases to enter into the combustion chamber. So we ensure that lean mixture is entered into the combustion chamber, and then we inject some quantity of air-fuel mixture into the pre-chamber, so it generates some kind of rich mixture. And once the rich mixture is generated, we initiate the spark, and then the combustion happens. And once the combustion is complete, we go for the exhaust stroke. So that's how the active pre-chamber system works. And here we I just took an example of ammonia combustion, and ammonia is enriched with your hydrogen as well. So the gray color represents your ammonia, pure ammonia, and this blue color represents your enriched ammonia with 20% of hydrogen. So this is correspondingly 5, 10, and 20%. So when you move with hydrogen enrichment from 0 to 20%, the ignition delay is drastically reduced by almost 70%. So the ignition happens here with pure ammonia, whereas with 20% of hydrogen, it is moved towards this side. So there's a large improvement. And we could also see that the slope of this combustion pressure curve is quite gradual when it comes to pure ammonia combustion, because its flame speed is quite low. Whereas with your hydrogen, the curve is steeper, right? So the pressure rise rate as well as the heat release rate is quite high. And because hydrogen has higher reactivity, it has higher laminar burning velocity, and it reduces the flame thickness, which aids in promoting the combustion for ammonia scenarios as well. And this shows the flame images, right? For different ammonia fractions. So this is for pure ammonia, the top one, and the bottom one is for hydrogen enriched ammonia. So ammonia is the flame intensity that we can see here. The flame intensity is less, whereas here the flame intensity is high, which means the combustion is happening at a faster rate. And the analysis of the penetration length shows that with pure ammonia, the development of the flame jet into the main combustion chamber is quite gradual, whereas with hydrogen enriched scenarios, it is quite fast. And the jet speed associated with it is also way higher when compared to your pure ammonia scenarios. It is like pre-chamber can enable advanced ignitions, right? It provides higher ignition energy, and it can boost the combustion of ammonia. But with that, you introduce hydrogen, then the improvement will be much more higher. That's what the outcome of this study is all about. And next is the second type of advanced combustion concept, which we thought I'll discuss today, is RCCA engines. I think with that, I'll just wrap it up. So time is about 8:40. So I'll just take at least 10 minutes more to finish off these things. So when it comes to RCCA engine, it is like you're injecting the fuel air mixtures into your inlet air manifold, low reactivity. So you have an ammonia cylinder. So the ammonia injector injects the ammonia into the inlet manifold, and we use high reactivity fuel. So here we adopted diesel injectors, and the engine specification is given. Majorly, it is a kind of diesel engine with the compression ratio of 17.5, and the engine speed and load is fixed. So they have analyzed the performance of the ammonia concentration variation in your RCCA mode under a fixed speed and load conditions. So this is example with the measurement with the combustion pressure, right? The black curve represents the case where with 0% of ammonia substitution, and the last one represents the 50% or 51% of ammonia substitution in diesel. Initially, if you see there is two peak in the heat release rate, and the first peak corresponds to the premixed combustion scenario, and the second peak corresponds to mixing controlled combustion scenarios. And if we go towards around 20 or 25%, there is a domination of premixed combustion phase over the mixing control combustion phase. So, and if you reach 50%, obviously the premixed is more dominant, and there is no scenario of mixing combustion. So, because the amount of diesel is highly replaced with ammonia. And coming to the combustion characteristics, we noted that the ignition delay is increased with ammonia substitution. So that is obvious because ignition delay of ammonia is higher. So if you are replacing a fraction of diesel with ammonia, then the ignition delay is higher. But the combustion duration, it gets reduced, and because whenever the pre-mixed combustion dominates, then the combustion duration reduces. And when we talk about the efficiency, the brake thermal efficiency, it's increased with introduction of substitution of ammonia. So it started with about 39% and it reached about 46% when we go with 40% of ammonia substitution. And the major factors behind higher brake thermal efficiency is your lower specific heat of ammonia mixtures, higher latent heat of vaporization, and diminished heat losses because it cools down the engines, right? And one thing to be noted is the brake thermal efficiency increased in spite of a reduction in your combustion efficiency. So this graph shows the combustion efficiency, and at 0%, the combustion efficiency nearly 100. With ammonia substitution, the combustion efficiency dropped to about 90%. So even with that, the brake thermal efficiency improved, and we can fine-tune the operating conditions so that the combustion efficiency can also be maintained at a higher level, so that will aid in improving your brake thermal efficiency as well. And the combustion efficiency as well as your exhaust gas temperature relates to the combustion quality. So, but both decreases with increase in your ammonia substitution, which means the combustion is getting deteriorated, and we need to fine-tune certain other operating parameters to improve its characteristics. And coming to the emission side, when ammonia is used in RCCA engine, soot emission is reduced a lot. So the black color curve shows the soot emission. So with increase in your ammonia concentration, the soot emission decreases. Similarly, with increase in ammonia substitution, ammonia emission increases as well. So there should be some measures to reduce things. And NOx emission, obviously, it reduces with increase in ammonia concentration because it reduces the combustion temperatures. And one more thing is when the ammonia gets combusted, it forms some kind of amino groups, so which processes the denitrification process. So even though nitrogen oxide is present, it reacts with ammonia, and it gets dissociated to form nitrogen. So the same thing happens in your SCR catalyst after treatment system. So you inject ammonia, and ammonia dissociate nitrogen to nitrogen and oxygens. So similar way that also happens during the chemical kinetics associated with your ammonia combustion. And final one is your N2 emissions. N2O emission increases with ammonia combustion. So that is quite a concern, right? So there should be a way to reduce the N2O emission as well. When it is with diesel combustion, N2O emissions is nearly zero for conventional fuel. So with ammonia, the pathway for N2O production is higher. So that has to be addressed. And in addition to that, we know that hydrogen has a problem or challenges with storage and handling. And in order to avoid that, people prefer to go with ammonia. And with ammonia, there are a number of problems when it comes to combusting ammonia because of its poor combustion characteristics. So now people have started finding out other way around, right? So you adopt some kind of onboard ammonia reforming, and this is one of the example paper published in Nature Communications, wherein they dedicated one cylinder for reforming your ammonia. So you inject ammonia into this reforming cylinder. So we adopt a very rich mixture into this. So during the combustion process, all the ammonia doesn't get combusted. So the high temperature encountered will dissociate the excess ammonia to hydrogen. So that is fed into your other three cylinders, right? So it is kind of in-cylinder reforming gas recirculation. We might have heard about exhaust gas recirculation. So this is kind of reforming gas recirculation systems. And what they could achieve is they could achieve nearly 84% reduction in unburnt ammonia and 87% reduction in your N2O emissions compared to the base engine, which is operated with ammonia. And when we talk about the efficiency, base engine has about 41.6% indicated work, that is the efficiency. And with the IRGR, that is in-cylinder reforming gas recirculation, the efficiency improved to about 45.6%, which is quite higher. So that's with the two different advanced IC engine concept, but there also exist different other advanced IC engine concept like partially premixed combustion mode, spark assisted compression ignitions, high energy laser ignition systems, post piston engines, multi-stroke engines, dynamic skip firing, and ducted fuel injection systems. I thought I'll give a glimpse of all these things, but it's almost time, so I'll just skip this part. Finally, the concluding remarks. So I had a picture. So nowadays people complain about technology, right? So they go with the usage of cell phone as restricted the communication between the people. So I have a clip, right, which is in the 1919 and 2017. That was somewhere in the street of London. So they use newspapers. Now they use mobile phones. That's the difference. And don't blame the technology, and try to effectively use it for the betterment of the humankind, now and the future, right? So I thank everyone for the patient listening, right? So if you have any questions, and
Sir, actually, my question is ammonia. You told ammonia is increasing efficiency.
Yeah.
Actually, due to higher latent of evaporation, in-cylinder temperature get reduced.
yes,
Due to that, the efficiency may affect break thermal efficiency.
true. You're asking about this studies, right? Yeah. So thing is, your insulin combustion efficiency depends upon a number of factors. So one is, as I said, your higher latent heat of evaporation will absorb the energy and it lowers your combustion temperature, which provides an advantage of reducing your heat losses to the surroundings. And one other thing is your ammonia air mixture has lower specific heat ratios. Your efficiency is proportional to your specific heat ratio as well. So which will also have an effect on the efficiency improvements.
Okay, sir. Thank you.
Any other doubts? Let me stop share.
Excuse me, sir. Higher amount of premixed combustion,
Yeah.
will it suits of the in-cylinder pressure or make some issues or not?
Yeah, the thing is, too much of premixed combustion may result in knocking as well. And thing is, everything has to be effectively monitored, right? So thing is, all depends upon how you ignite the mixtures. And as you pointed out, premix combustion, too much of premix combustion will obviously result in knock.
And also, I told that um, you have to advance the combustion, startup combustion, is it right? For
Your
ammonia.
ammonia, yeah. So the thing is,
Okay.
ammonia is kind of fuel with higher octane numbers, and it is like when we do the experiments, it's we try to achieve the maximum brake torque condition. So if you keep on increasing to a particular point and see how much torque improvement is there with respect to the advancement in your spark timing. And mostly for gasoline vehicles, it will lead to knocking. But with higher octane numbers, ammonia doesn't lead to knocking scenarios.
Okay. Um, uh, Start of heat release, will it be closer to TDC or some will it has because for each fuel naturally you have to look at
Yeah,
depends upon the lateral heat as well as the um, other factors. You have to set the start of injection. Is it, sir?
thing is, I said like we are looking for a maximum brake torque condition, right? So which means that if you are advancing your spark timing, we have to ensure that the combustion happens near to the TDC. Then only we'll be able to get the maximum brake torque. So if you advance the ignition timing further, your combustion will happen before the top dead center, and the work will be wasted. So that will not
Correct.
be
It will make negative effect.
Yes, true.
Thank you, sir. Thank you for your explanation. Thank you very much.
Thank you.
Sir, even I done in RCC engine only, my ammonia only.
Okay.
But I got actually advancing the injection timing, especially the ammonia, the PF injection. There's a duration reduced. But I got before PDC, whether it may get a negative effect or a positive effect, sir. That is a net rate.
So you mean to say that your combustion initiated before the top dead center, right?
Yes, sir.
Right. Thing is, ideally speaking, we have to look into the combustion phasing. So the 50% amount of fuel burn, and mostly if it is closer to 4 degrees after the top dead center, then it's fine. If it is below that, then it will have a negative impact on your engine power output as well.
Okay, sir. Okay. Thank you, sir.
Thanks.
Any other questions from the participant sides? If you have any further clarification, you can let us know. So the speaker is ready to answer your questions. Yeah, feedback form will be given shortly. So regarding application, how far you have reached, sir? The reality, practical applications.
So thing is, because we do research in ammonia as well as hydrogen, but thing is, I could have included a slide as well regarding the commercial implementation of ammonia and hydrogen engines. Majorly the truck manufacturers, they are keen with ammonia as well as hydrogen engine implementations, and majorly Ashok Leyland, JCB, and Tata Cummins, and people have launched their hydrogen engines, and ammonia is still people are working on it, because the major thing is you have toxic emissions, and
We will stop Pakistan.
sorry.
Yes, that is sir.
Okay. So ammonia is still under development, to be precise.
Okay, thanks. Recently, we heard, sir, that some reputed automobile company, rather than they are working on EV, they are focusing on hydrogen-based fuels. We heard recently in the news.
Yes, sir. Yes. Toyota has a longer history in working with hydrogen fuels, and Cummins also was working with hydrogen, and many people, majorly with Volvo trucks, everyone is keen on hydrogen because they feel that electric is a bit difficult to achieve with heavy trucks. But as I said, the future is not clear, so we have to have the different options. So people go with different options.
Sir, Toyota also working in a plug-in hybrid vehicle, sir.
Yes,
With a
yes.
regenerative braking system.
Toyota is the only company which has a wide opportunities. They work with all different alternate powertrains so that which is sustainable, they will adapt to that, and they'll create that platform in the later stages.
Sir, one more doubt. If you want to implement ammonia completely, what are the modifications we needed, sir? Up to how much percentage we can implement?
So, as I said, it's in the research stage development, and one thing that can be noted is if you go above 50%, the efficiency drops. But there are people who have done with, you're talking about ammonia RCCA conversion, right?
Yes, sir. Yes, sir.
So 50% after that efficiency drops. That's what from my personal opinion. But people are trying with different scenarios and trying to extract higher substitution as well.
Thank you.
Thanks.
Any more questions? I think for the most of us, it's high time to go to bed.
Yeah, because it's too.
However, we have a resourceful person with us, so that if you have any clarification, please let us know, so that we can spend some few minutes with you. Seems clear, sir. I think it's clear in the view.
Fine. Thanks. And I want to once again thank Dr. Manoj Kumar and the coordinator for this FDP, and Dr. Michael Joseph Stalin, the co-coordinator for this FDP. And thing is, it gives a good experience, right, to interact with people and share the knowledge as well. And I think I've sticked on to the time. Right, I thought it will get late, but try to manage within the given time frame. Thank you all for the patient listening.
Thank you, sir. Thank you so much on behalf of Adi Shankara Deemed University and my own behalf, as well as on behalf of all the participants. I once again thank you for spending your time, sparing your time and sharing your knowledge among us, sir. Thank you so much. We will be in touch with you, sir, in future aspects also.
Sure. Because I also forgot to mention the things as I was about to complete the presentations, right? So anyone, if you are interested in working with hydrogen or ammonia combustion systems, we are trying to build up a few things here. I am working on with pre-chamber ignition systems. One of my scholars has started with the flame visualization and spray visualization systems. We have a separate center for combustion and emission studies. So if you are interested, you can collaborate and come and visit our center as well. And if anything is required from NIT side, I'm happy to assist and help you as well.
Sir, pleasure, sir. Sir, pleasure to have you.
Thanks.
Thank you, sir. Thanks a lot.
Thank you.
Next.